Okay, so we've done translational partition functions and rotational partition functions. So today we're going to finish it out with vibration and electronic. Electronic is easy, it's just one slide. So now contrast this with like the two-level partition function. Remember we did those first. So really we've covered a bunch of different ones. Don't forget the two-level is sort of a standalone by itself. We talk about, or you might hear me when I'm in the video talking about a two-level partition function. I talk about molecules in the ground state, molecules in the excited state. Don't let that confuse you. I'm just saying particles, molecules, quantum things are in the ground and excited states. But a two-level system is not really a molecular partition function. It's not a translational or a rotational or vibrational partition function, which has all of these complicated formulas. Okay, it's just a simple table-based way to do it for two levels with degeneracy or three levels with degeneracy. You know, if you can easily count on one hand how many energy levels you have, then you can just do this problem from first principles with the Boltzmann factors. Does that make sense? We don't have to worry about the particle in a box or particle on a ring, rotation, or harmonic oscillator. We're not having to come up with any of those energy equations. We're just saying three levels separated by so many wave numbers of energy, right? So we're just told the energies of those energy levels. So those are not translation or rotation or vibration. They're just their own thing. So we'll just sort of set those aside, but don't forget, and don't be confused, I guess, is the thing. When you're thinking about a system that says there's three levels and they're all separated by 200 wave numbers, that's not any of these molecular partition functions. So you can just solve that one as is. The ground state is 0 energy. The first one is whatever I said, 200 wave numbers. The third one is 400 wave numbers. Start doing your Boltzmann factors in a table. Sum those up as your partition function. And then that's the denominator for all your probabilities. Okay. Sometimes you, like in the homework problem, that was a little confusing to people with this curve on there. But that's a realistic two-level problem. You've got this potential energy curve, and it has some local minima and some global minima. That's a two-level problem with degeneracy. Even though it's a molecule, it's just that dihedral angle that's moving around, and that dihedral angle is a two-level system with degeneracy. So we're going to get into the vibration and electronic partition functions today. Let me just check one more time to make sure it's recording. Yeah, okay. And so for vibrational motion, we have this harmonic oscillator energy equation, which is the vibrational frequency times the vibrational quantum number. So this is the quantum number, just to refresh your memory. And that's a V. Okay. And this is nu. The Greek character nu is the vibrational frequency. And the little tilde means it's in wave numbers. Okay. And we call this an equal ladder of states because it looks like a ladder, right? You have these energy levels that are equally spaced. And so that's one way to describe vibrational energy levels. Notice how that's in contrast to rotations, which would go up as J squared, or as the translations, the particle in a box goes up as N squared. These go up as just linear in V. So this is the default assumption for the vibrational partition function. We're not taking into account anharmonicity. We could add that in, but we don't in this particular part of the course. We just go with the straight harmonic oscillator energy equation. And this is the situation. If we don't have those anharmonicity constants, then this assumption fails a little bit. If we have internal rotation, again, the potential energy doesn't go up to infinity. Think about that dihedral angle. That's internal rotation of the molecule. And at the really cold temperatures, it would act like a harmonic oscillator. So if these are the two chlorines, and this is the carbon-carbon bond and dichloroethene, and they're 180 degrees from each other, they would oscillate like that. at really cold temperatures, they'd be in the ground state oscillating like that. But at high temperatures, they could spin all the way around. So that's not harmonic motion. That's, harmonic oscillator, the potential goes up to infinity. It would never get out of that well, whereas in this molecule, it just starts to spin around the inside bond at high enough temperatures. So that's where this assumption fails as well, this harmonic oscillator assumption. What that would do is it just would give you more energy levels that were populated. So it would change the statistics a little bit. So let's talk about the vibrational partition function. We know that partition function is the sum of all of the energy levels in that Boltzmann factor. And since it's an equal ladder of states, we start with equals 0, and then we go up to 1 times E over KT. Notice if we go up to V equals 2, that's 2 times E over KT. The next one will be 3 times E over KT. So we just get sort of a multiplication factor in the exponent. Now there's a couple of places where we would label it as 0. So V equals 0, if we set that equal to 0 energy, then we end up with this equation, right? We end up with E to the 0 over KT. But sometimes it's helpful when you're comparing molecules to each other to take into account what we call the 0-point energy. So to calculate this 0-point energy here, and that's the vibrational frequency divided by 2. So it's 1/2 of a vibrational frequency in terms of 0-point energy. In order to calculate that, we would set the 0 point of energy down at the bottom of the well. And so for harmonic oscillator partition functions, there's really 2 options. You could set, where do you put 0 energy? You put it at V equals 0 or at the bottom of this well. And there's certain situations where you would want to do that. We're not going to get into those, but you're going to see it in Gaussian. So I feel the need to talk about it in class, because otherwise you're going to be confused by what you see in Gaussian. And mostly it's when you're trying to compare like thermodynamics from molecule to molecule. Gaussian will calculate this part right here and give you that energy as a part of your internal energy. And then you need to add in the 0-point energies for all the molecules if you're going to compare apples to apples in like a thermochemistry calculation. You're going to do those next Monday and Wednesday. So you'll see this BOT in terms of your vibrational output from the frequency job. And I just want you to know here from this slide that means we're setting 0 energy down here at the bottom of the well versus that V equals 0 level. So let's calculate then the partition function. So this is, again, the sum. This is an infinite sum, because it's all of those terms. We know the energy levels, at least in theory, go up to infinity. When we're dividing by KT, they peter out. These Boltzmann factors become really small if you don't have a lot of temperature. But this is actually an infinite series that converges. Can you see the similarities here? So if we have, if X is equal to this piece right here, then this is that same piece squared. So that's X. This is X squared. You see it? This is X cubed. And if that's an infinite sum, that series converges to this. So this is an exact solution, not the assumptions we made for rotation and vibration. What did we do for those to get out of having to sum an infinite number of terms? Do you remember what we did for those? We turned it to an integral. So this is an infinite sum that just happens to converge. So we don't have to assume that our energy spacing is infinitesimal compared to the amount of temperature we have and everything like that. So at least for vibrations, this is great. We have an infinite sum. And so this is our result. I went ahead and inserted that energy term, HC nu. So And so this right here is the partition function for vibration at a given temperature. And so let's look at some of its properties. We imagine that the vibrational levels will become more populated at higher temperatures, like all the other systems that we discovered. And so here's the Boltzmann distribution probabilities of each state. And so they're shown here. And so this, at low temperatures, we have a partition function that's very close to 1, as we would imagine, right? As the temperature goes close to 0, the partition function converges to 1. As you raise the temperature, you get up to 3.86 for your partition function. And I think this is a kind of a confusing chart, and so we'll look at this for a second. Let's look at this orange, or what this row is trying to tell us. This is beta times E. So E over KT is 3. So what we're saying is that the E essentially is 3 times higher than the temperature. So we have a thermal bath, and this division here is too big, much bigger or larger than KT. Or you can think of it as sort of this vibrational temperature compared to the temperature is equal to 3. So our spacing in terms of temperature maybe is 100, and our temperature is only 33. So we're not quite have enough temperature to excite, but we do have some probability of excitation. Even though, if it's above absolute 0, you're going to have 1 or 2 molecules that are in the excited state. Because here's the thing. If something is at its ground state at absolute 0 and it increases its temperature, how could it do that unless some molecules were excited? Right? It couldn't be at a higher temperature than absolute 0 unless there were some excited molecules. So even though it doesn't have, on average, enough temperature to put molecules in the excited state, there have to be a few there, or it wouldn't be above absolute 0. So just probability-wise. And so if it's like 1 out of 100, it's going to be really cold temperature. Everything is at 0, and that one molecule is causing the average energy to be slightly above 0. And then you get 2 molecules in there, and the temperature rises a little bit. And then 3 molecules, and it rises a little bit. So you can't you can't raise the temperature unless you excite the molecules. And if you excite the molecules, you raise the temperature. So they go hand in hand. That's why it's so hard to cool things down. You have to de-excite the molecules. How do you force a molecule to drop to the ground state? What probes do you have? Well, light is one of them. And translational motion. So we put these things in a vacuum. The problem is you can stimulate emission, but you can also stimulate absorption, right? And so you really want to shield this from light so that it naturally radiates and then drops down. So then if the theta V, or the rotation, or the vibrational temperature, is equal to the temperature of the room, now this little bar graph is kind of representing temperature. And it matches that energy difference. So we have this theta V over T of 1. And now you've got molecules spread all over the place. So this is excited, this is excited, this is excited. So you have this is that Boltzmann distribution kind of on its side. Okay. What about 0.7? Well, that means that the temperature is a little higher than the vibrational temperature. And so then that Boltzmann distribution is spread out even more. And then here, the temperature is about 3 times higher than the vibrational temperature. So this yellow bar graph here is your thermal bath. Now that's how much temperature you have in the system. And then it results in this spread of molecules across all of these energy levels. This is a pretty good visual representation of the probabilities of being in all those energy levels. And so that's why I say in general all the time. Like when I say the partition function is in general a count of the number of levels that are populated. Look at this. It's not, it says 3.86 is my partition function, but there's a lot more than 4 levels that are populated. So that's why I say in general, it's more than the other 3, right? So here, this one at a higher temperature, we have more levels populated than at the lower temperature, and much more than down here. So that's why I say in general, it's a count of the energy levels that are populated. But is it an exact count? Like, do we have 3.86 energy levels populated? No, we have a lot more than that. But it's a way of thinking. If I have a higher partition function, more levels are populated. If I have a partition function of 1, I have 1 level populated. Okay. So down there, it's exact, 1. But as you get higher, it's more of a general trend. It goes up. Okay. So let's look at this complicated equation. And this is a skill I would like for you to be able to do, no matter what equation you're given, ever, not just in this course, to be able to read it like a paragraph. So as temperature goes to 0, what happens? So if I take this temperature, which is sort of in the, listen to everything that I can say about temperature in this equation. Temperature is in the denominator of an exponent, okay, that's in the denominator. Okay, so there's lots of places where it's buried, and we have to think about what happens if temperature goes to 0, that fraction that it's in blows up. Does that make sense? So this fraction goes to infinity when temperature goes to 0. So you should be able to walk your way out of this mess, out of the woods of this equation. So you've got temperature, it goes to 0. Then this fraction goes to infinity. All right. Well, I've got then e to the negative infinity. If you don't like e, make it 10. Okay. What is 10 to the minus 5? It's a small number. 10 to the minus 10, even smaller. 10 to the minus 1,000, really small. 10 to the minus infinity, 0. So something to the minus infinity is going to be 0. It doesn't matter what it is. It could be your lunchbox to the minus infinity. Okay. And then if that goes to 0, okay, then we have 1 minus 0 in the denominator and 1 on top. So the partition function goes to 1. So this is nice with an exact equation. We can prove, that at the low temperature, the partition function goes to 1. Let's do the same thing, but now let's make temperature go to infinity. So temperature goes to infinity. Then that fraction, what do you think the fraction does? The fraction has infinity in the denominator. It goes to 0, yeah. So I'm dividing by infinity. Okay, then I have e to the minus 0. So anything to the 0 power is going to be 1. So that piece goes to 1. And now that difference makes that in the denominator is important, right? E approaches 1, which means that I have 0 in the denominator and QV goes to infinity. So as temperature goes to infinity, the partition function goes to infinity. Maybe at a different rate, but it still goes in that direction. And then if temperature goes to 0, it's coming down, Q is coming down to 0, and right before it gets to 0, it turns and goes to 1. You see in the plot. So it's pretty interesting. So we could approximate this piece right here. It looks pretty linear, and in fact, you could just you could then just model it, 10 t over theta v. Okay. And so when t is greater than 10 times that vibrational temperature, we say the vibration is activated. So at high temperatures, what is high? That's what this red box is saying. This all simplifies to just the temperature compared to the vibrational temperature. Okay. Now, one thing that we haven't really talked much about is the fact that our partition functions, to get a total partition function, it's the product of all the individual partition functions. So it's not the sum. I mean, how would you combine all of these? You could add them together, or you could have a product. Well, it turns out that the product is the accurate way to think about this. So we have, where have you seen this before? Okay, last fall. That is the number of vibrations. And so for a molecule, it has all kinds of vibrations. It's got stretches and bends and twists and all of those things. And that 3n minus 6 motions, there's a partition function for every one. That means there's also a vibrational frequency for every one. There's a vibrational temperature for every one. Some are going to be activated, like these really low frequency modes, because the temperature is going to be 10 times that vibrational temperature. But like the CH stretch, it's never going to be activated. Not in our everyday considerations. So this is this capital pi. Okay, if you come across it pretty rarely. Capital sigma is a sum. This is a product. So capital pi is a product, and it's the product of all of these partition functions, starting with vibrational mode 1 and going up to vibrational mode 3n minus 6. And so this K over HC, we're familiar with that. Do you remember what the number is for that one? What's that? Yeah. 0.695, wave numbers per Kelvin. And then so whatever your vibrational frequency is on top, you can divide that. So what's the vibrational temperature for the CH stretch? I should have made a top hat with that question. Okay. So roughly CH stretch is how many wave numbers? I don't remember very many vibrations, but this is one I remember. Just what region of the vibrational spectrum? 3,000. Yeah, so 3,000 for the CH stretch. That should be something you could remember. Let's go ahead and turn up the heat. What is the carbonyl? 1,700, 1,600, 1,700. Yeah, so you could do these for all of these. What's the vibrational temperature for, let's say, the CH stretch? So 3,000 divided by 0.695. Notice you're dividing by something that is less than 1. So the number's going to get bigger. So it's going to be bigger than 3,000 wave numbers. So the vibrational temperature for the CH stretch is over 3,000 Kelvin. Did you get the number?
Yeah, I got like 4,000.
Yeah, so 4,000 Kelvin. And to activate that, like to really superpopulate all of those levels, you would need to be at 10 times that temperature. So you'd need to be at 40,000 Kelvin to activate the CH stretch, where it would just be irrelevant sort of what that frequency is. You've got molecules in the CH stretch all over the place. You're going to tear the molecule apart before you ever get to that temperature. Okay. But for something like the backbone motion in a big waxy molecule, so you have a C20 molecule, and you've got this really flexible molecule. Let's say that's 20 wave numbers, vibrational frequency. Let's make it easy. Let's make it 70 wave numbers, and we're dividing by 0.7. What would it be? 100? Yeah. So the 7's cancel, and we got 10 over 0.1, so it'd be 100. So 100 Kelvin would activate that motion. Okay. No, that would be, the vibrational temperature would be 100 Kelvin, so 1,000 Kelvin. Even that motion would have to be activated at 1,000 Kelvin. So, yeah, that would be, again, a 70 wave number vibration. You'd still need quite a large temperature for that. But it does happen. In fact, we can activate these vibrations and excite the molecule, and it can be torn apart. And that's what's happening in a candle. You're not really burning the wax. You're decomposing the wax by exciting all of these vibrations. And then the small molecules, the decomposition products, like an ethyl piece rips off of this waxy molecule and is a gaseous thing, and then starts reacting with oxygen, and that happens in the flame. So the heat from the flame melts the wax. Some of the wax is wicked up, and then it gets really close to the super high heat of the flame, and it just starts ripping off methyls and ethyls and butane groups and so on, and then those burn with the oxygen. And it's this whole process, absorbing heat, exciting the vibrational modes until the molecule rips itself apart. Yeah. And so then this same partition function, if you make the zero area the bottom, so this is V equals 0, this is BOT. So this is what Gaussian's using for the partition function in Gaussian for vibrational motion. Okay. So let's look at some of the Gaussian output. Here's our molecule, our asymmetric top, and here are the rotational temperatures. So this is kind of picking up where we were in the last lecture. We had these different rotational temperatures, rotational constants. Here's the 0-point vibrational energy. So that is the sum of 3n minus 6 frequency over 2 terms. So we have 3n minus 6 vibrational frequencies. Every one of those divided by 2 gives you all of the 0-point energies for each one. You add them up, that's the 0-point vibrational energy for this molecule. And then for the bottom 3 or 4 or 5 vibrational modes for a given calculation, I think it may go up to 5 or 6, it calculates the vibrational temperatures. So even for the very lowest vibrational motion in this molecule, which is probably that CLOH bend, so it's the bending motion for that hydrogen, that's going to be the lowest vibrational frequency. Yes?
Earlier you mentioned that the 0 point has either be a V1 or at the very bottom.
Mm-hmm.
Does it tell us which one that is?
Okay, so if we're calculating the 0-point energy, then we're setting the bottom of the well as 0, and then we're calculating the energy from the V up to the V equals 0 levels. So now those V equals 0 levels are not 0, they're 1/2 the vibrational frequency up above the bottom. Yeah, and so the Gaussian will calculate the electronic energy of the molecule, and then we have to add in the vibrational components by adding in all of these 0-point energies. Yeah. It's kind of funny when I heard Syndrome say that in The Incredibles. I use 0-point energy. I was like, that's not how it works. It's just vibrational manifold. If we set the bottom of the electronic well, because that's what gives us the harmonic oscillator shape, is the electrons and the nuclei interacting with each other. And then the atoms vibrate within those wells. So the bottom of every one of those wells, if you set those at 0, then you've got to add in that vibrational energy, because the molecule can't actually get down to the bottom. It hits V equals 0 and it can't go any lower. So we need to correct that energy by adding in the 0-point energy. So that's what's coming in here in the Gaussian thermal calculation, is this 0-point energy. Now, even this vibrational temperature, you see that's the lowest vibrational motion is still got 1,000 Kelvin vibrational temperature. Okay. So let's review how many degrees of freedom. In fact, I did this on a top hat, so let's go to that one. And let's see. There we are. Okay. So this is I've just picked ammonia. So I'm squeezing your brain a little bit. You got to know what ammonia is and how many atoms it has. Okay. So this is review. How many translational degrees of freedom does ammonia have? So think back, we covered ammonia a lot in the fall. It consists of nitrogens and hydrogens. I'll extend it for those that are logging in to Top Hat. Okay. And so you figured out ammonia, maybe, and then now you got to figure out translation. So you got to think about how many degrees of freedom are given over to translation. So what do we mean by translation? It's the motion of the molecule in space. So okay, that's 17 out of 17. Okay, 3, very good. All right, so that's the X, Y, and Z coordinates. So the whole molecule can move in X, Y, and Z. And hopefully I didn't confuse you by saying ammonia, but I mean, ammonia is the molecule, but it doesn't matter what the molecule is, everything, even my whole body with all its atoms can move in X, Y, and Z, and that's it. There's always and only 3 translations. Okay, good. Okay, let's do rotations next. How many rotational degrees of freedom does ammonia have? Okay. A lot faster answers. The shape of the molecule matters to some extent for rotation. It doesn't matter at all for translation. But for this one, you got to make one assumption about the molecule. Or recognize it. Okay. Okay, so here we go. So rotations, how do we define those rotations? Yeah, linear or not, it matters. And so it's rotation around X, rotation around Y, and rotation around Z. So Rx, Ry, Rz. Remember the character table. You had XYZ and Rx, Ry, and Rz. But you lose the Rz for linear. So if all the atoms are on a single axis, nothing's off axis, it has no moment of inertia off that axis, you wouldn't be able to tell if it was rotating. Okay. And then now for ammonia, we really do need to know the structure. So it's going to be NH3. So we really have to know the number and types of atoms, or just the number of atoms. This really is a lot faster than logging into Kahoot. Yeah. Okay. Waiting on one person. There you go. All right. Nice. Okay, so we have ammonia, NH3, that's 4 atoms. So 3 times that is 12. And then we subtract out the translations and rotations. So that's what the -6 is. So 12 minus 6 is 6. Okay. What is this? Later. Okay. All right. So we have 6 vibrations. Okay. Oh, darn. That was a great Top Hat session, but it's not on the video. So, so they'll be talking about it, but. And so, anyway, but this is, again, 3n total degrees of freedom, 3 translations, 3 rotations, and then we get 3n minus 6 vibrational degrees of freedom. In this particular molecule, that's 3 vibrational frequencies, and so that's why there's only 3 vibrational temperatures. But you notice how the vibrational temperatures really become irrelevant pretty quickly in small molecules. In larger molecules, you might have a lot that are low temperatures, but Gaussian really only calculates the bottom 5 or 6. So then Gaussian evaluates the partition function at the given temperature using the geometry and the vibrational electronic energy calculations. So this is the output of all of the partition functions that Gaussian calculates. And so now we kind of understand what Gaussian's giving us. That was the goal of these last 3 lectures, is to kind of get you an understanding for this thermochemistry section in Gaussian. We have the translational part, which is huge. and the rotational part was big, okay. But then up here we have the vibrations, and yeah, up here we have the vibrations. And notice how with V equals 0, it's essentially equal to 1, okay? Because all of the molecules are in their ground electronic state. Our first vibrational temperature was 1,000 Kelvin, so we're at room temperature. So we just don't really have any vibrational motion that's excited. Notice I've been saying this whole time that the partition function sort of bottoms out at 1, and yet here we have this one times 10 to the minus 5. So what that's trying to reflect is that I've got this is 0 here, and it's calculating the partition function for the number of molecules that are in V equals 0 here. So this partition function is really low because we're at a low temperature, and it's saying that all the molecules are down here. There's really no level there. And so it's sort of when it calculates the number of molecules that are in this level, it's saying, oh, there's really only 10 to the minus 5 molecules in the V equals 0 level. And so that's why this partition function is really low. Okay. We're never going to use that piece there, but it's there, and I want to explain it. So when people see this and they're confused by the partition function, I just wanted to sort of touch on that. So, okay. And so then that total partition function up here at the top is the product of all of these others, okay? And so we end up with, that 2470, which was the rotational, the like 14 million for the translational, the vibrational is 1.03, and then the electronic is 1. It's 0.1 with all those zeros times 10 times 10. And so then we end up with that. So that's our product of all of our partition functions. Now let's talk about this electronic partition function. So our temperature is going to be much, much less than our excitation temperature in electronic systems or in the electron cloud. We talked about most of our visible transitions are electronic. And I remember calculating in PChem 1 what kind of temperature would be necessary for a transition at 700 nanometers. So like the longest wavelength in the visible spectrum would require 20,000 Kelvin to excite even the reddest of the red peaks. Okay, so you're not going to have a molecule survive 20,000 Kelvin of temperature. Okay. So combustion temperatures are 1,500 to 2,000 degrees. And so if it's burning, it's not surviving. And so this partition function for electronic, because this KT is much, much less than delta E, essentially this is zero energy. This is e to the minus 0. And so this piece is essentially 1. And so all that survives is the degeneracy of the ground state. So that degeneracy of the ground state, here's our calculation. I said it was 20,000 wave numbers, it was 14,000. So, 14,000 wave numbers, which is 20,000 Kelvin. Okay, my memory's better than I thought. Okay. And so this, whatever the highest occupied molecular orbital degeneracy is, that's going to be your electronic partition function. You can't always assume it's 1. It might be doubly degenerate, like in... just take any one of those diatomics where you've got an odd number of electrons, like an nitric oxide, and you've got just one electron. It could be in the left orbital or the right orbital of that pi bond, okay, or the pi antibonding orbital. And so since you have 2 of those, you have degenerate levels. And if there's a way to make your electron configuration where they truly are equivalent in terms of spin-orbit coupling, then you're going to have a doubly degenerate ground state. In maybe a spherical system, something like methane, you might even have a triply degenerate electronic state. Okay, so that electronic partition function is just going to be whatever the degeneracy of that ground state is. So here's everything put together, and Gaussian takes care of all of this. Thank goodness. So we did our translational piece, which had that temperature to the 5/2. We have the temperature to the 3/2 here, and then where did this piece come from? Do you remember? Yeah, the ideal gas law, and this translation piece was the volume of the system divided by this thermal wavelength. Okay, and so this came from the volume. And so instead of trying to figure out what kind of volume you're putting your molecule in, let's just calculate the pressure. Okay, and so that's where that nRT. So this gives us another 2/2 temperature dependence for translation. So it's temperature to the 5/2, and we played around with that with some calculations. Then the rotational pieces has the symmetry number here, that sigma, and temperature to the 3/2 power again. That's pretty cool. The three rotational temperatures for A, B, and C. If it's a linear molecule, it will just have B and C. Okay. And then the vibrational piece, the product of every 3n-6 vibration. And then that electronic piece, the degeneracy of the ground state. Now, I have Kahoots listed on here, and that's just to indicate there are Kahoot questions that you can take. So go on to Kahoot, and if you want to study and review, you can search Chem_Prof and find all my Kahoots. This would be listed if you wanted to sort all of the ones relative to this course. Just search for 4449. And all of those Kahoots have 4449 in the title. And then you'll be able to see Kahoots related to the translational partition function and the rotational and the vibrational. So you can practice that way, test yourself. So thank you, Gaussian, for doing all this. But that's, if I just throw that equation at you, what a bear, right? And so we've now gone through what these theta A and theta B mean, and the crazy temperature dependence of all of these different population of energy levels based upon temperature in a molecular system. So translation, rotation, vibration, and electronic. Okay, now there are some supplemental pieces. We've got about 2 minutes. Let me just hit you with a couple. If we take an ensemble or a collection of identical units, and a molecule is a perfect example. So if we have a mole of molecules, each molecule is kind of an identical unit. And so we'll have some molecules excited, some molecules not excited. And again, we're doing statistics on this ensemble. So this is like a whole course dedicated to this. So I would say don't take any notes until I tell you to write something down. but in terms of finding the overall partition function, remember that the partition functions are multiplied by each other for a particular molecule. What if I have multiple molecules? Well, they're multiplied by those two. So for the whole system, it's that molecular partition function for water times the next water molecule times the next water molecule and all of that, because that's the denominator for all the possibilities in the system. So it's the number of molecules is the exponent. So if I have 5 water molecules, I have the partition function, and it would be that times that times that 5 times. And so we just raise that number of molecules to the exponent, or raise that partition function and put the number of molecules in the exponent. So that's the key that you need to know right now. And so so you can see here, connection of capital Q to little q. Little q is for an individual molecule. Capital Q is for a set of molecules. And the number of molecules shows up as an exponent. Now, in order to prevent overcounting, because those molecules are identical, we reduce that partition function by the number of molecules factorial. Now, that's a big number. In fact, your calculator even on your phone or computer, can't do much more than like 70 factorial, 80 or whatever. I think I don't know. Try it out on your calculator sometime. Put in a number and do the factorial, then put in the next higher number and it'll say error. Okay. You can find it, and it's not very many. So once we get to like 20 or like 100, say, molecules, we can't even calculate that in without making an approximation. So that's where this last piece comes in. This is called Stirling's approximation, and it's a way to get rid of this exponent. So the reason I tell you all of this is because I want you to remember that it's sort of the number of systems up here as an exponent. So that's an important piece. And they have this this divide by n factorial, which is going to blow up on us. And so we have Stirling's approximation. And one way to get rid of that is to take the natural log. And this is the Stirling's approximation to get rid of that n factorial. So we will come back to this, but and when we come back to this little exponent is just going to appear out of nowhere, and that's why I wanted to talk about it today. It's like when we go to an ensemble, all of a sudden we have the number of particles as an exponent. Okay, and this gives us a hint as to where we're going. When you come up with the equilibrium constant, what do you do with the concentration of the species? It's if there's like free water molecules in the calculation, it's the concentration of water to the third power. That comes in from this. Like this are the roots of that. And so we'll develop that further. So it's kind of interesting to see the number of particles as an exponent. And that's where it comes from, the statistical counting of the population of energy levels when we go to an ensemble of identical molecules. All right, so we'll talk to you more next time. I did set up my office hours on Monday and Thursday at 10. So there's a link in Blackboard. And again, if you can't fit either one of those in your schedule, email me and we can do an individual Zoom, okay, whenever it's convenient for you, if our schedules work out. So.